Hello everyone, welcome to Digital Lesson for Students by Department of School Education, Nagaland. I am T. Pungudi, MSc MPhil Mathematics, your math tutor from CD King Higher Secondary School, Jotsama, Kohima. In this session, we are going to learn exponential and logarithmic functions. Okay, so here I have drawn different graphs. If you see this graph y equal to x, it's a straight line, isn't it? This is the y equal to x. This is the straight line we get. And if I raise the power to 2, see here y equal to x, we get straight line. And y equal to x squared, slightly steeper than that straight line, right? And again y equal to x cube, we get steeper again. Then y equal to x power 4, so the curve gets steeper. When we increase the power, higher the degree of the polynomial, we get steeper the curve. If we get the steeper the curve, what do we mean is the rate of the growth is getting greater. Okay, rate of the growth is getting greater. See, like in this pandemic situation, we can express this pandemic situation in the form, these functions. Okay, these are called exponential functions and I'm going to define it later. See, and there is a question now, is there any function which goes very faster than any other polynomial? Yes, it is. That is the one y equal to 10 to the power x. So this is the steeper curve we get among all these polynomials. See, suppose if we take f3x as x cube, all right, x cube, and suppose and this curve as f of x as 10 to the power x. If I give x equal to 3, we get f3 of 3 is 3 to the power 3, that is 27. But here if I give 3, so it becomes 1000. See, it's much greater, right? So we get the steeper curve here with this 10 to the power x. Now we can define the exponential function, that is an exponential function with base b greater than 1 is the function y is equal to fx is equal to b to the power x. Okay, this is called exponential function. Y is equal to fx equal to b to the power x. This is called exponential function. All right. When we increase the power of x, we get steeper the curve. Okay. So, for example, we can use this function in to study about the pandemic situation. We can use this function to study about the fire, which spreads very aggressively, right? Increases rapidly. So, we can study those things using this exponential function. And also spoilage of food, the microorganisms in culture, they double every hours, right? You have studied in bio. So, in this case of studies, we can use this exponential functions, which increases very rapidly. All right. Okay, there are some properties with this. We will see one by one. If I take the base, this is the base, all right. So, if I take the base as 10, okay, 10 to the power x, this is called common exponential function. Common exponential function. Okay, and if we take this base as e, already we have studied about this e value, that lies between 2 less than e less than 3. It is between 2 and 3, approximately 2.71828. It was introduced by Leonhard Euler. So e to the power x. If you change the base as e, this is called natural exponential function. Natural exponential function. And what about the domain and the range of this function? This b to the power is defined from set of all real numbers to the positive real numbers. Positive real numbers, because we get always positive values. When you expand this, if you give any values of x, you will always get the positive values. Okay, so therefore the domain is the set of all real numbers and the range is the set of all positive real numbers. Okay, and one more thing, this point, no, 0 1 0 1 0 1 0, 1. This point is always on this graph, okay, graph of the exponential functions, because x equal to 0, you will get always 1, whatever the value of base, right? So this 0, 1, the point will be always in the graph of the exponential function, and it is ever increasing. If you look at this graph, if you increase the value of x, the graph will automatically rise. That means it gets steeper. So it is always increasing function. And also, if you take the x values, then very big non-negative values. That means if you increase the values of negative, then it will get closer and closer to the x-axis. That means the function will go near to 0, but it never touches the x-axis. Okay, it just goes, it leans on this, but it never touches the x-axis. Okay, these are the properties we have to remember in case of exponential functions. And we have already studied in class 11, the derivative of the exponential function using the first principle is e to the power x. Okay, so d by dx of e to the power x equal to e power x. And one more you have studied, d by dx of a to the power x equal to a to the power x log a. Right? Please remember these two derivatives, we will be using it in our exercise problems. Okay, let's move on to the logarithmic functions. Okay, now next is logarithmic functions. We define the logarithmic function as like this. Let b greater than 1 be a real number, thus logarithm of a to the base b. Logarithm of a to the base b, we denote like this. Logarithm of a to the base b, we write like this, is x. It takes the value x if b to the power x equal to a. If it is true, then we can write this one as log of a to the base b. Actually, exponential and logarithmic functions are mirror images. Mirror images means they are inverse of each other. Therefore, log of a to the base b is equal to x if b to the power x equal to a. Okay, how we use this one? For example, 2 power 3 is 8, right? So instead, if you know this value and you want to find out the power, so you can write like this, log of 8 to the base 2 is 3. See, here x is 3 and b is 2, it is written here, and 8 is here. Okay, in such a way, this logarithmic function is helpful for us. So we use this one to study about the earthquakes and sound, all those things for this logarithmic functions. Okay, and here also we have common logarithmic function and natural logarithmic functions. Okay, if you take the base as 10, this base, no, if you take it as 10, log 10x, 10a, no, for example, this is called log x, no, x. Then this is called common logarithm. Common logarithmic function. So common logarithm. And log, if you take the base as e exponential, that is e value between 2 and 3, that is natural logarithm. We can write this one as simply log x, or you can write ln x. Okay, in any of this you can use the symbol to represent the natural logarithm. So this is natural logarithm. Natural logarithm. Often we see this notation in our book, log x. Log x means it denotes the natural logarithm, that is the base is e. Alright. Okay, here also we have properties, and this logarithmic function is defined from opposite, that is r plus 2r. Okay, its domain is always the positive real numbers and the range is always the set of all real numbers. Okay, and it is also ever increasing. This is also ever increasing function like exponential function. Okay, and the third point is this common logarithm, natural logarithm, done. And if you see the graph, so this graph goes like this. So therefore, this 0, 1, 1, 0 is always in the graph of log x. Okay, so this is y equal to log 10x, and this is log ex, and this is log 2x, for example. Okay, when we increase the value of, when we approach x, here x, no, when we take nearer to 0, this is origin, right? Then the graph tries to meet this y-axis. Okay, but it never meets y-axis. Okay, and if we increase the value of x, the graph gets steeper. That means it is increasing. Therefore, we say that it is ever increasing. Okay. And the e power x graph goes like this. Okay. Y equal to e power x. This goes like this. And y equal to x. The straight line passes through like this. Okay. Therefore, this logarithmic function and the exponential function, we say that they are mirror images and reflects on y equal to x. All right. Okay, these are the properties we have to remember when in case of logarithmic functions. And what is the derivative of log x? We study about natural logarithm. Log x is 1 by x. Okay. So I suggest you people to have a formula book and writing all the derivatives, and then whenever it is necessary you can go through and learn it. If you are not writing in a book and keep it ready, then you have to search everywhere. No, the derivatives often you have to flip your pages and then find out the derivatives. Better you maintain a formula book. Let's move on to the exercise problems. The first one is differentiate with respect to x e to the power sine inverse of x. Let us assume this as y equal to e to the power sine inverse of x, right? So we are going to differentiate with respect to x. So in this case, this y will give us dy by dx, that is equal to derivative of e power x is e power x, right? So it will be e to the power sine inverse of x into, then we differentiate sine inverse of x, right? So this is by chain rule. What is the derivative of sine inverse of x? 1 by root over 1 minus x square. That's all. This is the answer. E to the power sine inverse of x divided by root over 1 minus x square. Okay. This is the required answer. The next problem is sine of tan inverse of e to the power minus x. Here also we have to use the chain rule, which holds the function, entire function sine. First we will differentiate this sine, then we will get inside the bracket, then we differentiate tan inverse, and then we differentiate e to the power minus x, and then we differentiate minus x. So 4 steps we have to go. So let y is equal to sine of tan inverse of e to the power minus x. So differentiate with respect to x, we get dy by dx is equal to, derivative of sine is cos. So cos tan inverse of e to the power minus x. In place of x we have this one, right? So sin x derivative is cos x, okay, into, then derivative of tan inverse of x is, if you remember, the derivative of inverse trigonometric functions, tan inverse of x is 1 by 1 plus x square. All right. So 1 by 1 plus x square. In place of x we have e to the power minus x. Therefore, e to the power minus x whole square. Okay. Into, then we differentiate e to the power minus x. So what is the derivative of e power x? Derivative of e power x is e power x, isn't it? So e power minus x. So it will remain the same, e power minus x, into, then we have to differentiate minus x. I already told you, if you differentiate a variable with respect to the same variable, we get 1. But here minus x is there, so we get minus 1. Okay. So if you write in order, then that gives you an answer, book answer. Minus e power minus x cos tan inverse of e to the power minus x whole divided by 1 plus e to the power minus 2x. That's all. This is the required answer. Okay, the next problem is root over e to the power root x, right? So we will differentiate this one. Y is equal to root over e to the power root x. So this can be written as e to the power whole power, e to the power root x whole to the power half, right? Easy to differentiate. That's why we write in this way, root half in the power. Then differentiate with respect to x, we get dy by dx is equal to, here also we apply the chain rule. First we differentiate the power, then we get inside, we have to differentiate the base, then we differentiate e to the power x, then we go to root x. Okay, so 3 steps we have to do. First let us differentiate the power, that is 1 by 2 into e to the power root x whole to the power half minus 1, right? n into x to the power n minus 1. Okay, into. Then we differentiate this e to the power x. Derivative of e power x is e power x. Therefore, it remains the same, e to the power root x into. Now we have to differentiate this root x. Root x, how do we differentiate? 1 by 2, because it should be treated as half x to the power half. So 1 by 2 x power half minus 1. Okay, so this will be half e to the power root x whole power minus half into e to the power root x by 2 into, here half minus 1 is minus half, so we can write it in the denominator root x, right? So if I put together all these, e to the power root x by 2 to the 4, and inside the root x, because this is also minus half, in denominator we get root over, so we combine these two as e to the power root x. Okay, so this is the required answer. Then one more problem, that is, let y equal to cos of log x plus e to the power x. If we differentiate with respect to x, we get dy by dx is equal to, first let us differentiate the cos and then we get inside the bracket and we differentiate 1 by 1 term wise because it is in addition. So we differentiate separately this one and then this one. So derivative of cos is minus sine. So minus sine log x plus e to the power x. Okay. Here we have to treat this one as x. Okay. Then derivative of cos x is minus sine x into, then derivative of log x is 1 by x plus e to the power x derivative is e power x. Okay. If you take the LCM, you get x. So it will be, if I write this one in the beginning, you will get x e to the power x plus 1 into sine log x plus e to the power x. So this is our required answer. That's all. So here in this session, we learn exponential and logarithmic functions, and also we have seen some exercise problems. In the next session, we will learn how to differentiate parametric equations. Thank you.